between a recursive and explicit definitions. Example 1, given the recursive definition, an that is equal, the first term is a 5, and a common ratio is 1.5, and this is the previous term. So now let's take some information from here. A1, A sub 1 is equal to the 5. So this is 5. And just let's take, and the R is 1 over 2. So the common ratio is 1 over 2. And now we're looking to find the A2. What is A2? A2 is equal with the A1 times 1.5. Or this is equal with A1 times R. And what about the third term of the sequence? The third term is equal with A2 times 1.5. So the common ratio. But what was a A2? A2, we are looking here, for example, A2 is equal with A1 times R. And instead of A2 here, we are plugging in A1 times R times 1.5. But 1.5 is R times R, which is equal with A1 times R squared. Times R squared. Now if we are going to the fourth term, what is going to be the fourth term? The fourth term is equal with the previous term according to the recursive formula times R. But in this case, what is the third term? This term here. Let me write a third is equal with A1 R squared. So instead of A3, we are substituting A1 R squared. A1 R squared times R, and this is equal with A sub 1 index 1 R cubic. Even if you look at A in the fifth, A sub 5, A of index 5 is going to be A sub 4 times R. So this is a recursive formula, a recursive definition of the geometric sequences. And again, A4 is equal with A1 R cubic, equal with A1 times R cubic times R. And now A in the fifth, A sub 5 is equal with A1 times R4. So can we generate from these patterns now the general form or explicit general form of the explicit definition of geometric sequences? Can we generate now? So if we are looking here, the sub, the index number here, the index number here signifies n here. But if you look at the exponent for here, the index here is one unit greater than the exponent. For example, here is 4, here is 5, the exponent is 3. And now, if we are looking here, for example, in the fourth term, here is 4, but the exponent here is 3, 1 less. If we are looking in the third term, here is a 3, n is equal to 3, but the exponent is equal with 2. 1 is less than the term here. And if we want to generalize this form, so if, for example, A is in a term n, the current term is equal with the A1, so the first term never changes, The first term is a1 time r, the common ratio, but the exponent is 1 less than the term here, the number of the term. So the exponent here is 1 less the number of the term. It means n minus 1. So this is the formula to explicit formula of geometric sequences. But this has a big advantages because when we solve some problems, we just plug in the number of the term and we can find out what term it is. For example, if we're looking for the term 50 or 100, we don't have to find the previous terms. We need just to know the first term and the term what we are looking for, 100, we plug it in, and the common ratio, and we can find right away. With the recursive formula, we have to find 100, for example, 100 previous terms until we get to 100. Otherwise, we cannot solve it. It takes a long time. But this has a big advantage over the recursive formula.